Welcome back. In this video, we're going to solve problems 6, 7, and 8 from the review sheet. Here's problem 6a. We're going to find the arc length of the curve y equals the natural log of x from x equals 1 to x equals e. So this one's just a matter of applying a formula. So what we're going to need is we're going to need to take the derivative. So I guess we should name the function, call it f. It's the natural log. Its derivative is 1 over x. And we're going to need to take the derivative, square it, and then add 1. And then we're going to take the square root of that. And that's what we integrate. So we're going to integrate from 1 to e. So this is going to compute the arc length. We will integrate the square root of 1 plus the derivative squared. So 1 plus x, 1 over x squared dx. Okay, we can rewrite this as the integral from 1 to e of the square root of, well, it's 1 plus 1 over x squared. We can write that as x squared plus 1 over x squared by making common denominators, and then rewrite this further as the integral from 1 to e of 1 over x times the square root of x squared plus 1. Okay, so I think it makes sense to try a trig substitution. We see the x squared plus 1 underneath the square root. So we're going to let x be tangent of theta. Dx will be secant squared theta. D theta. All right. We're going to leave the limits in terms of x for now. I think that makes the most sense. So when we do the substitution, we end up with an integral from x equals 1 to x equals e. The 1 over x I'm just going to write as 1 over tangent theta for now. And I'll have when I plug in x equals tangent theta into square root of x squared plus 1, I just get secant. So I can actually write that, I guess, here. Whoops. Secant theta. And then I multiply by the derivative, which is secant squared theta. D theta. So to evaluate this integral, the next step is kind of tricky. What you need to do is take this secant squared theta and write it as 1 plus, we're going to write it as tangent squared theta plus 1, and then multiply secant over tangent times tangent squared plus 1. We end up with an integral. The bounds are the same. Tangent squared times secant over tangent is just going to be secant times tangent. And then I have plus 1 times secant over tangent. So secant is 1 over cosine. Tangent is sine over cosine, so I'm dividing out the 1 over cosine part. And then I'm left with 1 over sine, which is cosecant. Okay, so now I've moved this expression up here, and we're going to continue to evaluate. I have an integral. Well, actually, now I can write down antiderivatives. I know that the antiderivative of secant times tangent is just secant theta. And for cosecant, I have the natural log of cosecant theta plus cotangent theta. D theta. Or, sorry, no d theta. There would be a plus c if I was doing an indefinite integral. But this is a definite integral, and we're going to evaluate from x equals 1 to x equals e. So now I remember, we'll write back in here, we took x to be tangent theta. So I draw this triangle. Whoops. Label one of the angles by theta. And then label the sides so that the tangent of this angle is x. So I put an x here and a 1 here because tangent is opposite over adjacent, and then I can fill in the hypotenuse as x squared plus 1. Now I can write secant theta, so is 1 over cosine. Cosine is adjacent over hypotenuse, so secant will be just hypotenuse over adjacent, so x squared plus 1. And then I have the natural log of, this should have actually been an absolute value sign. It won't matter for our problem because our limits are positive and everything else should be positive, but I'll write them in here. So cosecant is 1 over sine. That's going to be square root of x squared plus 1 over x. And then cotangent is adjacent over opposite, so plus 1 over x. And I'm evaluating from x equals 1 to e. And when I do that, I'll write out quickly what we get. We're going to get a square root of e squared plus 1 from this. I can rewrite this natural log term as the natural log of the numerator, so x squared plus 1 under a square root plus this 1, minus the natural log of the x denominator. When I plug in e, I'll have a natural log of 1 as the natural log as the natural log of x term. So this is going to be plus the natural log of the square root of e squared plus 1 plus 1, and then a minus 1, which is dividing by the natural log of x when I'm plugging in e. And then I'm going to subtract from that what I get when I plug in 1 to this expression. So I'm going to have minus the square root of 2, and then minus the natural log of the square root of 2 plus 1. Okay, so I realized after I solved this problem that I messed up the sign here. This should be a negative sign in front of the natural log, which would make this a negative sign. This would make this into a negative sign, and it would make this into a plus sign. Okay, just a sign error. The rest of the procedure is fine. Okay, for 6b, we're going to take the same curve over the same bounds. So our function, again, is the natural log of x. We're dealing with it from 1 to e. But now we're finding the surface area obtained by rotating this segment of the curve around the x-axis. So, around the y-axis. Okay, so since we're doing that, it might help to draw a quick picture. So here's y equals the natural log of x. It's equal to 0 at x equals 1. It's equal to 1 at x equals e. So since we're revolving around the y-axis, not the x-axis, we want to rewrite this as a function of y. So this is y equals 1. So we're going to take y equals ln x, rewrite it as x is a function of y. We get x equals e to the y. And so we'll be taking this and revolving around the y-axis. The bounds on y will be from 0 to 1. So we get, for our surface area, the integral is the integral from 0 to 1 of 2 pi times, so we take the function, which is e to the y, and then we have the square root of 1 plus the derivative, which is also e to the y. We square it. Okay, so here's the thing we're taking the derivative of, the integral of. So to evaluate this integral, we have to do a couple of substitutions. First, we're going to let u be e to the y. So then du is also e to the y dy. So now we're looking at the integral from, I'm going to just keep the limits as they are, y equals 0 to y equals 1. I have 2 pi times this e to the y dy is just going to become du, and I have the square root of 1 plus u squared du. To evaluate this integral, we're going to use the trig substitution. So again, we're going to use tangent, u equals tangent theta. And so du is secant squared theta, d theta. And keeping the bounds in terms of y, I have 2 pi times, this is going to be secant theta, and then du is secant squared theta, d theta. Now the problem has become one of finding the antiderivative of secant cubed theta, d theta. I'm going to leave this to you to work out on your own. It's not trivial, but there's lots of resources. I think this integral has its own Wikipedia page if you want to go check that out. You have to do a combination of trig identity usage and integration by parts. But when you get it, or when you do it, you get, sorry, not an integral anymore. You have, we'll have 2 pi. The antiderivative of secant cubed is 1/2 secant theta tangent theta plus 1/2 the natural log of secant theta plus tangent. And we're evaluating from y equals 0 to y equals 1. Now I need to evaluate this. Remember, I need to plug in what I had before. Let's recall that I had u equals tangent theta, so we should undo this substitution first. To do that, it's just like the previous problem. I draw a triangle, label one of the angles as theta, and then put u over 1, and then the hypotenuse is u squared plus 1. So we have, I can cancel this 2 with this 1/2, so I have pi times secant is 1 over cosine. Cosine is adjacent over hypotenuse, so I have square root of u squared plus 1 times tangent, which is u, plus the natural log of the absolute value of square root of u squared plus 1 plus u. And we're evaluating still from y equals 0 to y equals 1. And now recall that we set u to be e to the y. So plugging that in, we get pi times the times, in parentheses, the square root of e to the 2y plus 1 times e to the y, plus the natural log of those two terms but added, so e to the 2y plus 1 plus e to the y. And now we can finally evaluate from 0 to 1. So maybe I can write it as one big expression at the bottom. Pi times, I plug in 1, I'm going to get e squared plus 1 times e. Well, this is actually, there's a square root, so I'll write the e first times the square root of e squared plus 1 plus the natural log of the absolute value of square root of e squared plus 1 plus e. And then we'll subtract what we get when we plug in 0. So we'll have, this will be 1, this will be e to the 0 is 1 again, plus 1, so I'll have a square root of 2. And then plus, or sorry, minus, because this we're subtracting the term when we plug in 0, minus the natural log of the square root of 2 plus 1. And there we go. Here's problem 7. The setup is we have a cone filled with water. Its height is 8 feet, and its diameter is 20 feet, so its radius is 10. And we're pumping all of the water from the cone up to the top of the cone, and then up an additional 6 feet. You can imagine it's out some pipe at the top. The first thing we're going to do here is impose a coordinate system. So I've chosen that we'll take y equals 0 at the bottom. At the top of the cone, we have y equals 8. And then above, at where the water is exiting, we have y equals 14, which is, of course, 6 plus 8. Now, the way we go about solving problems like this is we consider, for y between 0 and 8, we consider a slice of water that is, say, delta y thick. So thickness is delta y, and it's a height y above the bottom of the cone, or the, yeah. And what we're going to do is compute the work done picking up this slice of water and moving it out to the top of the pipe, and then we'll sum over all y, or all slices of water, taking a limit as y goes, or delta y goes to 0, which turns the sum into an integral. Okay. So first step is we're going to find the radius of this slice. So I'm going to draw this auxiliary picture, which is the same cone, just depicted from the side. Oops. Here's my slice. And then labeling some of the pieces. The radius is 10. The height of this thing is 8. I'm going to call this r for just now, this radius of the slice, and then I know that this distance from here to here is y. So using similar triangles, comparing this big triangle with height 8 and width 10 to the smaller one with height y and width r, I find that r over 10 is equal to y over 8. And then solving for r in terms of y, I get r is 10 over 8 times y, or 5 over 4 times y. So this is the radius of the slice. So that means that the volume of the slice is going to be the area, which is pi times r squared, times the thickness. So we'll say the volume of the slice will be the radius squared, so 5 over 4 times y squared multiplied by pi times delta y. If you care about units, this is in feet cubed. Okay, so we have the volume. Now we're going to multiply by density to find the mass. We're given the mass of water as 62.4 pounds per feet. So we're going to take our volume, delta y, and multiply by 62.4, which this is the units of density are pounds per cubic feet, so we're multiplying that by something with units cubic feet and we get pounds. So this is mass pounds, I guess. Oh no, let me correct that. This is force pounds. So we're already taking into account the acceleration due to gravity when we're multiplying by this. So okay. So this is not the mass, this is the weight, or otherwise known as the force due to gravity. Now, okay, so now we know the force exerted by gravity on our slice, the distance that it has to go is from a position of y from the bottom of the cone all the way up to a height of 14. So the distance traveled is 14 minus y, meaning the work that we do on this slice is the product of the force and the distance. So writing it nicely, I'll have pi times 62.4 times 5 over 4 squared times y squared, multiplying by 14 minus y, and then finally delta y. So the units of the units here was feet, and then the units here is foot-pounds. Okay. So that's the setup, which I think is the hardest part of this. I'm going to erase this so I have room to write. To find the actual work done on the entire thing, we're going to integrate essentially this expression, but with a delta y replaced by dy. So the idea is you add all of these slice works done, and you take a limit as delta y goes to 0, using knowledge about Riemann integrals that you know that this will turn into an integral. The integral is defined from 0, which is the bottom of the cone, to 8, which is the top. So 0 to 8. And then I have all those constants, where I believe I left out the pi. Oh, and the pi's there, sorry. I have all those constants, pi times 62.4 times 25 over 16 times y squared times 14 minus y. And then we have a dy. So I trust that you could do this integral by yourself. I'm not going to spend time in the video doing it. All this is constant. You're really just integrating y squared times 14 minus y. What you end up with is 418,208. The answer key says this with an 81 decimal place, but really if we're doing this to correct significant figures, we see that the best we have is really one significant figure. So if you wanted to be really correct. You'd only write this as, for instance, 400,000. But anyways, the units are foot-pounds. For problem number 8, we're finding some limits. The first one is one that we look at. If we kind of take the limit of the different pieces as n goes to infinity, we have 1 inside the parentheses, and then infinity as the exponent. So this is of the form 1 to the infinity, which we know is one of these indeterminate forms. So to do this limit, sometimes what we do is we write, like, let's say like y equals 1 minus 1 over n to the nth power, and then we take the natural log of both sides. What I want to do instead is exactly the same procedure. I'm just going to do it without defining a new variable. I'm going to write this as e to the natural log of that expression. Right? Observing that this didn't actually change anything because e to the natural log of whatever is whatever, because they cancel. Now I can take, since e to the x is a continuous function of x, I can take the limit and bring it up inside the exponent. So I have e to the limit as n goes to infinity of the natural log of this expression, which now I'm going to apply log rules to. I have the natural log of 1 minus 1 over n times, there would be an n here on the outside, but I'm going to bring it downstairs and write it as 1 over n. Okay, so I skipped a bunch of steps going from here to here maybe, but you can take some time and check that these are really the same. The reason I wrote this as a 1 over n in the denominator is I want to apply L'Hopital's rule. I see that as n goes to infinity, I have the natural log of 1 minus this goes to 0, so I have natural log of 1, which is 0. And on the bottom, I also have 0 as n goes to infinity. So this is 0 over 0. So I use L'Hopital's rule, and I take the derivative of both the numerator and denominator of this fraction. I still have e, and I still have the limit as n goes to infinity. But now here I have a 1 over, right, differentiating a log of something, I do 1 over the something and multiply by the derivative of the something. So the derivative of 1 minus 1 over n is 1 over n squared. And then in the bottom, I have the derivative of 1 over n, which is negative 1 over n squared. I don't have a negative sign here because I multiply by the minus sign that was on the inside. So I have 1 over n squared here, and here they'll cancel, and I get e to the limit as n goes to infinity of just this last piece, 1 over 1 minus 1 over n. And now I can take, just take the limit as n goes to infinity. This term will go to 0, and I have 1 over 1 minus 0, so minus 1. And then my answer is not minus 1, it's e to the minus 1. So remember, we kept this e along the whole time. And there. Okay. Problem 8b is actually also a L'Hopital's rule problem in disguise. The first thing to do is write it like this, as the limit as n goes to infinity of the integral from 1 to n of 1 over x dx over n. So it's easy to see that as n goes to infinity, the denominator goes to infinity. To see that the limit as n goes to infinity of 1 over n, the integral of 1 over x, the integral from 1 to n of 1 over x dx. Well, okay, you could just evaluate this yourself, but you could also notice that this is just the definition of the integral from 1 to infinity of 1 over x dx. And this integral diverges. So this also limits to infinity. Now, to do L'Hopital's rule, we're going to take the derivative of the top and bottom with respect to n. If you really want to, you can write it as x as a continuous variable, the limit as x goes to infinity, the integral from 1 to x of, and then you have to use a different variable, say 1 over t inside the integral, and then we have x on the bottom. You don't have to do this, but the reason I'm writing it this way is to make it clear that when we're taking a derivative, this should look familiar. We're going to apply the second fundamental theorem of calculus. So I'll write it here because in parentheses I'm going to say, remember that the derivative of the integral from 1 to x of 1 over t dt, this is just going to be 1 over x. I take the x and I plug it into the integrand where I see t. This is the second fundamental theorem of calculus. Okay, so on the top, I have 1 over x. On the bottom, I have 1. And so I see that I'm just left with 1 over x as the limit. And as x goes to infinity, I get 0. Okay, you could have done this without the fancy fundamental theorem of calculus business. You could have just integrated this from 1 to n. You'd get the natural log of n as the numerator, and then you have ln n over n, which of course will go to 0. But I don't know, I thought this was a better way to do this problem, because it didn't require you to be able to integrate the thing here. Problem 8c is probably my favorite problem in this entire course, because it combines a lot of different concepts throughout the course. So the first thing to notice is that this is actually not an infinite series. The reason for that is, okay, we're used to taking infinite series by looking at it as a limit of partial sums, meaning we take a limit as the upper part of a sum goes to infinity. The problem is, in an infinite series, the terms don't change with n. They're only allowed to change with the indexing variable of the sum. So you can't use series techniques to look at this. Instead, the first thing you might think to do is to use some logarithm rules to simplify the summands here. So we have the limit as n goes to infinity of the sum from k equals 1 to n. This nth root I write as an exponent, right? I can write it as 1 plus k over n to the 1 over nth power. And since there's a natural log here, I can write 1 over n times the natural log of 1 plus k over n. Next, you stare at this piece for long enough and you realize that it's a right-hand approximation, or right endpoint approximation to an integral. So going all the way back to the beginning of the course when we were talking about Riemann sums, we had a formula that looked like this. We had delta x, which was b minus a over n, multiplied by a function evaluated at a plus k times delta x. So once you make that recognition, you see that, okay, here the 1 over n is the same as b minus a over n, meaning b minus a has to be 1. This piece here is a plus k times delta x. So we can say that a is 1, meaning b is 2, and then I have k delta x, right? 1 over n is delta x. So in other words, what I've recognized is that this is a right endpoint for approximation for the integral of a function where a is 1, b is 2, and the function, the thing that we're plugging in a plus k delta x to, is the natural log of x. Okay, so, and now that we have that, we're taking a limit as the number of subintervals in the approximation goes to infinity. This will converge then to the integral from a to b, so the integral from 1 to 2 of the natural log of x dx. Okay, so to evaluate the limit, we really just need to evaluate this integral. I remember that the antiderivative of natural log of x is x times the natural log of x minus x, and I'm evaluating it from 1 to 2, meaning I'll get 2 times the natural log of 2 minus 2 minus 1 times the natural log of 1, which is 0, minus 1. So 2 ln 2, we can write that as the natural log of 4, because this 2 can come inside as an exponent. Natural log of 4, and then I have minus 2 here, minus a minus 1, so that's just minus 1. There we go. So we use some log rules, and then definitely the hardest part of this problem is recognizing this as a Riemann sum, which I think is extraordinarily challenging if that's not already in your head. But once you do, you can work out that it's really an integral from 1 to 2 of the natural log, and then we have to use integration by parts if you don't have the antiderivative of natural log already memorized. You use integration by parts to find it, and then we plug in and we get our answer. For problem 9, we're doing series analysis. So the task for all of these is to determine whether the series converges or diverges, and if it converges, does it converge absolutely or conditionally? Okay, so for 9a, we have the sum of natural log of n over n cubed. So this is a positive series, meaning if it converges at all, it converges absolutely. To analyze it, we notice that on the top we have the natural log of n, and that is always less than n for n bigger than or equal to 1. And now if we take this inequality and divide the top and bottom by n cubed, we find that our sum n at natural log of n over n cubed is less than n over n cubed, which is 1 over n squared. So we can do a direct comparison with this series with the sum of 1 over n squared, which is a convergent P series. So we summarize by saying, since sum of 1 over n squared converges, and if you want a reason for that, it's a P series with P equal to 2. So does the sum of the natural log of n over n cubed, and we say by direct comparison. So I think this is a good way to write your answers to series convergence problems. All right, just a sentence looks like this. For 9b, we're looking at the sum of the natural log of n divided by the natural log of the natural log of n. So before you try to think of a complicated test to do, we should always check whether the limit of the nth term is 0. So we're looking at the limit as n goes to infinity of the natural log of n over ln n. And we have, as n goes to infinity, ln n goes to infinity, and then so the bottom will go to infinity as well, meaning we have a limit that we can use L'Hopital's rule on. We have the limit as n goes to infinity. I take the derivative of ln n with respect to n, and I get 1 over n. And then on the bottom, I have 1 over the natural log of n, and then by the chain rule, I need to multiply by the derivative of the bottom here, which is 1 over n. And this simplifies to the limit as n goes to infinity of just natural log of n, because the 1 over n's cancel, and then this is in the denominator of the denominator, so it actually ends up in the numerator. And this limit is infinity. Okay, so the nth term of this does not go to 0, and so the series natural log of n over ln n diverges. And the reason is by the, well, you call it the divergence test or the nth term test. Okay. For 9c, we have the sum of -1 to the n times n squared plus 1 divided by 2n squared plus n minus 1. So your intuition here is to, might be to say, all right, I have n squared on top with this -1 to the n, and then roughly n squared on the bottom. The smaller terms don't really make a difference. And so this will behave like n squared, will behave like -1 to the n times n squared divided by 2n squared, which is the same as -1 to the n over 2. But we have to be careful with that. Remember, when we ignore small terms to do this kind of series analysis, we're implicitly using limit comparison. And we can't apply limit comparison to this series because it's alternating. But that should tell us something, right? The thing that I just wrote down and then erased. If I was looking at this sum, this diverges because it fails the divergence test. So that should give us a hint for what to check for this one. So we should apply the divergence test again. And we notice that for large n, n squared plus 1 divided by 2n squared plus n minus 1, so in other words, everything except for the -1 to the n, is going to be close to 1/2, because that's the limit of this term. This is a 2 and not a 7. meaning that this sequence behaves like minus 1 to the n. And we know that the limit doesn't exist. So that's not like sound reasoning, just as it's on its own, but you can say like something like, for large n, the sequence oscillates between positive and negative. This is just one way to express it, but I think this is fine. Oops, positive and negative, and those numbers are not going to 0. They're numbers close to 1. Okay, so this limit doesn't exist, therefore the series, which I'm not going to write again, diverges. For 9D, we have the sum of arctangent of n squared divided by n squared plus 1. Looking at this, we see that the top, as n goes to infinity, arctangent of n goes to pi over 2, so this is a constant on top, divided by something that is roughly n squared. So that should tell us that we should do limit comparison with the sum of 1 over n squared. So we'll do that. We're going to take the limit as n goes to infinity of this, arctangent of n squared over n squared plus 1 divided by 1 over n squared. We can rewrite this as the limit of n squared over n squared plus 1 times arctangent of n squared. As n goes to infinity, this term goes to 1 because I have two n squareds as the leading coefficients on the top and bottom. And arctangent of n, as I mentioned, goes to pi over 2, so this is going to go to pi squared over 4. So I've done a limit comparison of the general term of this series with 1 over n squared, and I got a number that is bigger than 0, meaning that this series will converge because the sum of 1 over n squared converges. So since this series converges, whoops, so does the one above. And if you want to give a reason, which you should, the reason was limit comparison. Or you could have announced beforehand that you were doing a limit comparison with the sum of 1 over n squared. For 9e, this one's kind of tricky. We have the sum of the log base n, so the log is changing with n, log base n of n factorial divided by n cubed. The first thing, off to the side, I'm going to do a little bit of scratch work. Log base n of n factorial. I can write this as the log base n of n times n minus 1 times n minus 2 and so on until I get to 1. So I'm just writing out the factorial. And then since this is a logarithm, I can write it as the sum of the logs of these terms. So I have the log base n of n plus the log base n of n minus 1 plus and so on until I get to the log base n of 2 and log base n of 1. All right, now we're going to do a comparison, a direct comparison. So here we notice that, okay, log base n of n is 1, meaning the exponent to which I raise n to get n is 1. The exponent to which I raise n to get n minus 1, since n minus 1 is less than n, this number is going to be less than 1. And indeed, actually, all of these numbers are less than 1. So the entire thing is less than 1 plus 1 plus, whoops, there should be a 1 here. So this term is equal to 1. All the rest are less than or equal to 1. So, and I have n terms, so this is equal to n. So what I've shown is that the log base n of n factorial is less than n, meaning the log base n of n factorial divided by n cubed is less than n over n cubed, which is 1 over n squared. So the comparison was more complicated, but just like in the first one, our series converges because it is less than the sum of 1 over n squared. So the series converges. By direct comparison to the sum of 1 over n squared. For 9f, we have the sum of a sequence an, and an is defined recursively. We know that the first term is equal to 2, and then each term besides the first one is obtained from the previous by multiplying it by 6n plus 1 over 5n plus 3. So recursively defined sequences like this are easy to handle with the ratio test. So I'm going to do the limit as n goes to infinity of the absolute value of an plus 1 over an. And once you write this down, maybe it's easy to see why this will work out. Everything's positives here, so I can ignore the absolute values. An plus 1 is expressed as 6n plus 1 over 5n plus 3 times an, and I'm dividing by an. So these terms will cancel, and I'm just left with the limit as n goes to infinity of 6n plus 1 over 5n plus 3, and this is equal to 6 over 5. So 6 over 5 is bigger than 1, so the series diverges by the ratio test. Okay, that's the end of this video. The next video will probably have the entire rest of the solution, so stay tuned.